prices and inefficiencies in data markets. Take it away. You have until 10:50.
Thanks very much for your invite. So I'm going to talk about too much data, prices, and inefficiencies in data market. This is a joint work with Darren Asamoglu, Aso Zaglar, and Annie Maktoumi, who is in the audience. And if you have any questions, you can ask him. Okay, so the motivation of this talk is the fact that we know our lives are much better by using the technologies that are around. So we can like lively broadcast this talk because of the technology. And we regularly use these products. We do not even bother worrying about why we're using these products. We're using Facebook, Twitter, talking about it proudly. So these applications and products are founded and funded by data. What do I mean by that? So every day they're being improved by the data that are gathered from us as the users. And they're becoming a higher quality technology. And at the same time, their revenue is generated by our data. So basically by the advertisements or by explicitly selling data, they are generating revenue. So now the heavy usage of the data in the recent years brought the public awareness about like the privacy issues and the scandals around it. So in particular, the Cambridge Analytica data scandal was one of the famous ones who made the public become aware of like the issues of the privacy. And the questions regarding the regulation that should be and whether there should be laws around the privacy. So in particular, if you were also listening to the Mark Zuckerberg going to the Congress, one of the questions that was going around was that, what is the appropriate model for the data market? So in order to answer that question, some things we should understand about the data market and what are the features of the data that makes it unique. So one of the features is that the first fact is that there's no unified definition of the privacy. And in fact, the people are not aware of how much value they have for the privacy. And on top of that, how their data is going to be used and by whom it's going to be used. And at the same time, the third factor, which will be the focus of this talk, is the fact that actually there is a high correlation among the data of different people. So even if you do not want to share your data, if some other people that are correlated with you are sharing their data, probably some information about you without your consent will be leaked. So in this talk, I'm going to actually focus on, let me make sure that this is yes. I'm going to focus on this third bullet. So we would like to understand how this correlation will affect the equilibrium prices. And in particular, we would like to know whether there are any equilibria that are beneficial for both the user and also the platform. And what are the implications of these markets for the personal data? So if you have a data market, how would this affect the users and the platform? And how can we improve it? So the main question is whether we should treat privacy as an economic good, like a commodity, just normal market for commodities, or whether we should actually put regulations and actually treat it as a right, not as something that you want to sell. So what I'm going to do in this talk, we are going to talk about a very simple model of data sharing. So this is a stylized model of data sharing by one user, where when you're sharing your data, some relevant data about the others will be also revealed. And we assume that the platform wants to buy the data from the users in order to infer the type of the users. We basically first establish some information measure and then study the equilibrium existence of this game. After having the existence, we are going to characterize the equilibria and also the efficiency properties of this. We are going to provide the conditions under which the equilibria will be efficient or inefficient. And we then look at the generalization, of course, when, for example, you have competition, when you have multiple platforms, when your values are unknown to the platforms, or when even the correlation matrix is not completely known. At the end of the talk, after learning more about the equilibrium, we are going to see what are the schemes that we can use in order to regulate this market and what are the possible approaches. Okay, so there is a large literature which I'm not going to dive into, but if I want to categorize it, I will actually say that one main category is the related literature in the privacy, which is in the law literature, as well as in the, so it's going back to ages ago in the law literature, and also it's in the economics literature. There is also the information market that where you're basically selling and buying the data. And then there are like some, if you want to look at the externalities, I would say that the early articles are going back to the McCarthy and Fairfield and Engel. So these articles are basically talking about the externalities, and some more recent works on the data externality and information market are these papers. So I'm not going to dive into the details of these papers for the sake of time. So let me jump into the model. So we assume that we have end user. These are the data holders that are residing on a network. And each user has a personal type. So for example, you have a personal preference of political affiliation. Okay. So this is your type. I will denote it by xi. This is coming from a Gaussian distribution. And users' types are correlated with each other. So this correlation is going to be represented by matrix sigma. And as a platform, what you want to learn is this x's. So you want to learn the types of the users. So how can you do that? You're going to offer a price. And in exchange for that price, what you will get back from the user is some data. So what is that data and how is it related to the type? So data is SI, which is a noisy version of your type. For example, in your profile, you're going to actually like some pages. Those are not exactly your affiliation, but they are going to actually say something about your type. So SI is going to be the data that will be shared by you in exchange for a price.
Sorry, does the network have any role beyond, go back, does the network have any meaning beyond just being the correlations in sigma? Or, okay, you're just, it's just, and you're not making any assumptions that the sigmas are 0, 1, it's just an arbitrary correlation.
Yeah, yeah.
So the price you offer me has no impact on the algorithm.
No, it doesn't have any impact. So I will explain the actions in the next slide. Yeah.
The way sigma appears is sigma inverse in the likelihood of x. So should I be thinking of the network as sigma inverse, or the support of sigma inverse, or the support of sigma?
So this is the covariance matrix among the types. So it's just the covariance matrix.
Okay.
Like you have like the xi's, and the covariance matrix that shows the correlation among them is defined by this sigma. Okay.
I have 2 questions. One is, this data that they give, does it have a single observation of xi?
A single observation SI, you mean? Yes, you will have one SI.
Just one observation. Yeah. And then the second question is, those like edges are just there to reflect that there is
this. Yeah, this is just to represent. So it's not really like the network, social network. It is the correlation matrix. That's all. Okay. Yes.
So are there zeros when there's no edge?
There is no, yes.
And the zeros in sigma, not in sigma inverse.
Yeah, it's in sigma. Yeah.
And then the last question is, are the ZIs also going to be correlated, or they're?
No, they're independent noises. So ZI, I didn't write it in this slide. So ZI is an independent noise. Okay. Okay. Now we have now let's actually see, now that we know what is the type of the user and the data, let's see what you can do. In this network, we are assuming that the only action you can take is whether you want to share or not to share. And so you reside on there, everybody's on the Facebook, let's assume. And you have the option of like whether you want to let your data to be shared by the with some application on Facebook or not. So we are denoting the action of sharing by AI. So if this is whether you want to share your personal data, and the set of the users who are sharing their data on the platform, I'm going to show it with the calligraphic S of A. Okay, so these are the people who are actually, those are the data that are shared on the platform. So this is what the platform will see. So now we are reaching to the part that I want to define what is my, what is this data that the platform is gathering, right? Or what is this information that I'm getting from you? So I will define it as the reduction in the mean square error. Okay, so at the beginning, I have for example, sigma I square. And then when the people are sharing their data and I'm sharing my data, there will be a reduction in my estimator. So this mean square, the reduction in the mean square error is the leaked information of the user I. Okay, so this is the part, this is your part that you will care about your privacy. So this is the part that will show up in your utility, as well as the part that will show up in the platform's utility, as we will see. So just to give you an example, it's possible that, for example, you do not share your data, but some information will be leaked, right? Because there's a correlation, right? So here you can see that agent 1 decided not to share. So A1 is 0, and 2 and 3 are sharing. And since there is a correlation between 1 and 2 and 1 and 3, some information will be leaked. Now, let me also define the payoff. So your payoff as the platform will be what? It will be you care about the total leakage. So if you have higher total leakage, you will have a higher utility. So it would be the summation of leakage over all individuals. And you are going to pay a price for buying those data, so minus the prices that you paid. Now, the payoff of the user, how do we define that? So as a user, you have a value for privacy. So I will denote that value that you have for privacy by VI. So if you share your data, I'm going to pay a price. So the platform is giving you PI, but some information about you will be leaked. So you're going to lose some value VI times the leaked information. So this is your utility if you share your data. And if you do not share your data, you do not get any price back. And some information will be leaked about you. So it would be minus VI multiplied by the leaked information. So you can see the difference of these two is just that you are also taking this action 1. So this information leakage is potentially higher here, right? And if I want to look at the surplus is the summation of I will consider the summation of the platform and all the users in the world together. So that would be my social surplus. So if I sum up, we can see that the prices will cancel out. And what is left is the summation of 1 minus VI times the leaked information. So that would be my social surplus. So far, these are just the definitions. Now let's actually jump into the definition, more definitions. So let's actually also look at the solution concepts. So the user equilibrium is defined as an action AI, which maximizes your utility considering the actions of all other agents. So of course, this could be for a given price vector. This could be not unique, right? So depending on the actions of the others, you can also have another equilibrium. So we are going to denote the set of all user equilibria corresponding to a price vector by calligraphic AP, okay? Now, we will show actually a few properties of this information leakage that we define. So the first property, we call it the submodularity. So basically what it means is that as more users are going to share their information, the marginal leakage is going to be decreased. So you can see that you can assume that when people are sharing their information, something will be known about you. So when you are sharing more data, the margin will actually have a less effect, a smaller effect. So we call this submodularity. So let's actually look at this example and effect of this submodularity. So consider the price vector P1, P2, and P3. And suppose that at the beginning, agent 2 decided to share, while agent 3 decided not to share. At this point, potentially, agent 1 may not share. Now, if you have this submodularity property, if 2 and 3, both of them will share, now it can happen that one will be now willing to share. Why? Because the marginal leakage that you will provide by sharing is going to be decreased. And as a result, you may actually now be willing to get P1, right? So as a result, this is like the implication of the submodularity. So if a larger set of the users decide to share, then I will be more willing probably to share, right? And it probably reminds you of the supermodular games, which we will see in the next slide.
Marginal increase of information leakage decreases.
Mhm.
I don't really understand that. What you said in words makes sense to me, but what's written there?
What this words?
I guess the marginal increase in what?
Marginal increase of information leakage. So if you share, the marginal information leakage will increase, right?
This I function.
Yeah, this I function, it's going to be increased by an extra share, right? Now, suppose that a superset of agents will share, right? Now, again, if you share, this marginal will increase, but this increase is less, right? So that is the submodularity, and this is also, you can see it in this example. So if 2 people are sharing, now if I share, I know that my information, I will share extra information. But this shared extra information is lower than in this situation. So as a result, I will be willing to get P1. Okay. And yes.
It's partially connected down. So not have too much effect on.
Yeah, exactly. So, but still you will be submodular, right? It could be less effective, but still it will not be the other way around, right? So, and this submodularity property, I wouldn't say that it is for any sort of information leakage, but for the mean square error, it holds, and also for some other interesting ones. Yes.
So from the perspective of the platform, there's a decreasing marginal returns from buying information. And so from the literature of, the convexity or concavity of the value of information, we know plenty of counterexamples, right, where we see that little information might not be useful. Once you get a certain amount, it becomes useful. Stiglitz, Masrani, Smith. And so those would be instances of information models where the monotonicity would go the other direction.
So that's actually very interesting. Yes, I agree. So for this model, then we have the monotonicity as we show and the submodularity, but as you mentioned, it's not without loss of generality. It's not about any solution concept and any distributional assumption. And then the other property that we can see here is monotonicity. So probably monotonicity holds. The submodularity is the case that will not hold. So monotonicity of the information leakage, it means that if more people are sharing, the more information will be revealed about you. So this is a very natural property. Now, having these 2 properties, as you can guess, we can see that the user equilibrium exists. In fact, the set of the user equilibria forms a complete lattice, and it is non-empty and it has the largest and smallest element. And the proof idea, as you could see in the previous example, and you could guess, is that we said that the leaked information is submodular, or in other words, our game will be a supermodular game. So as a result, we can use the Tarski fixed point theorem to show that it has a lattice structure and smallest and.
Sorry, what's a complete lattice?
Sorry, what?
What is a complete lattice?
So it has so you can define the joint and the max and mean action on any 2 elements of that. So for every 2 equilibrium, you can define a max and mean. And for all of them, there exists. And then there will be a unique maximum and a unique minimum. So now we are going to define the Stackelberg equilibrium. So this is for the user equilibrium given a price vector. Now, as the platform, you are supposed to choose the prices and the people are supposed to act on it. So the notation of the equilibrium that we will use is the Stackelberg equilibrium, where an action profile A and a price vector P is a Stackelberg if, first of all, the actions are belonging to the user equilibria set, and moreover, the utility that the platform gets on that action profile is the highest among all. potential actions in that user profile and potential prices. So this is like the highest that the platform could get out of the user equilibria, possible user equilibria. Is that clear? Any questions? Yes. This is like sender preferred, if you want to say. This is like the sender preferred in the information design literature.
So it's the platform optimal second equilibrium.
Exactly. Okay, so now when we know that the user equilibrium exists, this one of course exists because it's the maximum, right? So for any sigma and v, the Stackelberg equilibrium exists. Okay, so now we have the existence. Now we should actually see what are the properties of this equilibrium. Okay.
Sorry, when you say the Stackelberg definition, you're also making, I'm sorry if you said this, are you also making a selection that it's the platform?
Yes, 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 yes. Yeah, and that's why I said that, of course, it exists because I take the maximum, right? Any questions? Okay. So now let's actually, before I jump into some real properties, let's actually go over a few examples together. So the first thing I want to see is that whether the total payment monotone in the set of the users who will share their information. So let's actually start with a very simple example. You have two users, everything is symmetric, they have the same value, and there's a correlation of rho among them. So if I want to draw the user equilibria as the function of the price vectors, we are going to have a figure like this. So we have four regions. So in the blue region, so when the two prices, both of them are high, both users will share. When both prices are low, nobody will share. If one of the prices is high, the other one is low, then one of the users will share. And you can see that there is an overlap between these two regions, of course, right? Because we have multiplicity for each price. Okay, now, so far, so good. Now, let's suppose that I'm actually going to increase the correlation among the two users, okay? So as I'm increasing the correlation, this region becomes bigger, right? At the lower price, you're willing to both share your data, right? So at some point, what will happen is that this is the price, the price that we will pay to the same price on this line. I'm paying the same price to both of the users at the same time, right? So when I'm getting to this line, what I can see is that, so at this point, I'm paying the same prices here and both users will share. Let's actually increase a little bit the correlation more. So now what I can see is that at this point, I can in fact get an equilibrium where both users will share in this region, right? And at this price when the price was higher, when the price was higher like this, at this price, I could not get both of them share, right? So you can see a non-monotonicity in the, if I like the total, in the total payment, right? So here I'm having a lower total payment while both of the users will share my equilibrium, okay? So this is one thing that we can see. And the other example is we would like to see whether the surplus has any sort of monotonicity, whether increasing or decreasing in terms of the value that you have for the privacy. So again, consider that two user example. So what we can see in the Stackelberg equilibrium is that actually the surplus will have a shape like this. So what happens is that if the values of the user is very low, in particular less than 1, where 1 is the value of the platform for the data, then the surplus is positive, and as you increase the value, the surplus is going to decrease. So it's going to decrease until here. Now, when you pass 1, still it's going to decrease, and it's becoming in fact negative in this region until some threshold. When your value is higher than something, then both users decide not to share anymore because their value is sufficiently high. And then all of a sudden it becomes 0, right? So you can see that, again, it's not either increasing or decreasing. So these are just two examples. So now let's see whether we can say anything meaningful, like any sort of result. So, yes, go ahead.
So if the platform approached them and opposed to simultaneously. So here the prices are given simultaneously.
Exactly.
So instead, if I could approach one user and then make them a take it or leave it offer on the price and then approach the second user afterwards.
That's probably,
It should
so
improve based on better.
so since I'm taking the highest equilibrium, I'm not sure if it's gonna improve it, right?
Yeah, so that's what I'm wondering. Is the highest equilibrium equivalent to the, because people still deviate away from, right? So like if I had a sequence of people, somebody in the middle has a different choice in the second problem than they do in the next.
Yeah, it's not obvious. I would guess that actually the highest one is doing better than this one if I go sequentially. So I want to convince them one by one, depending on the notion of the equilibrium that you want to define for the sequence. But I don't think that you can do better than that because you get all the possible externalities from others. So for example, I can convince both of them to share at a zero price, right? While if I go sequentially for the first one, if I want to ask them to share, it depends on how I want to, unless I want to look at the simultaneous move games, I don't think that they would share, right? So I can actually deplete the price to zero, basically, if the correlation is sufficiently high. Now, if I want to go sequentially, it's not clear for me whether they will share in the first round. So
I guess they still know that the other person will share in a second, so it's.
So it will be like simultaneous then, yeah? So but that's a very good question. We haven't thought about it to pin it down, so.
I think this might be a way to implement uniquely your outcome.
Yes.
You were setting. My sense would be that
Yes.
that your way of doing it sequentially would uniquely select that as a unique something imperfect.
Actually, yes, that's a very good point because also that will be easier to justify and explain, right? So thanks very much. Okay, so now let's actually look at see whether we can do any characterization. So the first thing we will do is that we're doing the easiest thing, price characterization. So suppose that I know who I want to share. Let's see whether I know I can pin down what will be the price that I should offer. So the price that I should offer to an agent to share, if I want them to share, should make them indifferent between sharing and not sharing, right? That's the best thing I can do. So as a result, the price that I will offer is the difference of the leakage if you share, multiplied by their value for privacy, okay? Now, the question is that what is this value, or can we say anything based on the matrix properties? So let's actually call the information leakage that is caused by others, that for others means that if you do not share and the others decide to share, let's call that the network effect. So what we can show is that the leakage that if you share, the leakage will be basically the summation of the network effect that's caused by others, plus some terms that I call it user effect. And this is basically in terms of the sigma I, as well as this network effect, okay? So I can write it additively. And in particular, I can even show more. So your price, you can actually write it in closed form. So your price will be, we said that it is the difference of the information leakage of whether you share or not, multiplied by VI. So VI multiplied by this value, as we saw in the previous slide, where the information, the network effect actually can be characterized completely based on the correlation matrix, considering the agents that we decided to share, okay? So if I fix the action profile, this price that I should offer is actually going to be completely characterized in the closed form setting, okay? So, so that's good news because usually if it was in networks, we don't have closed form solutions. Yes.
Should one interpret the variance of each user?
So the variance, so basically, so I don't know much about you, right? So I have some prior about you, right? I will say that your data is coming from a Gaussian distribution and it has some, like it's going to
Right, from an informativeness point of view, like is a higher variance user more informative?
Less informative, right? If the variance is higher, so I'm looking at Gaussian. If the variance is higher, I know less about
But
it.
like if
If the variance is zero, I completely know your value.
right,
but
so then it's not valuable for me as a platform, right?
Yeah.
If your variance is zero,
Yes.
it's less informative.
Yes. Yes. I'm trying to decrease that variance, right? So if it's zero, nothing to gain there, right? So now what we can see here is that prices are increasing in sigma I square. This is what you were asking. And also prices are decreasing in the set of users who will share their information, right? Because if more users are sharing, it's going to be depleted. Now let's actually go to the inefficiency result. So something that will be important for the inefficiencies is to define like these two sets of low value users and high value users. So I will call the users who have value less than 1 for the privacy low value and the rest high value users. So one thing that you can see easily is that all low value users are going to share their value, share their data in the Stackelberg equilibrium. And why is that? Because even if there was no externality, if it was nothing there, still the platform was willing to buy it, right? If it was just like they were singletons sitting around, the platform still will buy them, right? Now we know that with the externalities, the prices will be even lower, so I will buy them, right? So as a result, in any Stackelberg equilibrium, all low value users are going to be to share their data. Now, using this property, we can actually get some inefficiency results. So the first thing is that if high value users are uncorrelated with each other and with the low value users, then the equilibrium will be efficient. So that is good news. So this is the case that these are low values and the correlation is only happening here. For high values, they're just singletons sitting around, okay? However, if there is a correlation between the high value user and the low value users, then there is a threshold for this value that if you pass that threshold for the high value users, then you will have inefficiency. Similarly, even if you don't, as the high value user, if there is no correlation of high value users with the low value users, so they have nothing to do with the low value users, and their correlation is only among themselves, still there is a mid-range for the values of the high value users that if you are in that range, we can show that inefficiency happens. And the reason is this one is exactly because of this externality properties, right? Because they have externality, even though their value is higher than 1 for the privacy, they know that their information will be leaked. And as a result, they are going to share their information, even though they know that their utility will become negative. Even if they don't share, it's negative, but it becomes even worse. Now the question is, given these things, we want to see whether the data markets are beneficial, or in other words, is it better to shut down the data market or keep it? So that's the question. By beneficial, that's what I mean. So in order to understand that, let's actually put a simple bound on the social surplus. Okay, so the social surplus that we get, recall that the social surplus was 1 minus VI times the information leakage of each user, summation over OI, right? So if you are a low value user, this term is going to be a positive because 1 minus VI is a positive thing. So this term is a positive thing. So I will put the upper bound on the information leakage to maximize its magnitude, right? So this is less than or equal to 1 minus VI, summation over I in the low value users, times the information leakage if I assume everybody will share. And if you are looking at the high value users, I know that this term is negative. So basically, if I want to find an upper bound, I'm going to minimize the information leakage. We know that all low value users, no matter what, they're going to share. So I'm going to put the VL here. So this is an upper bound on my social surplus. Now, if this is negative, this upper bound is negative, then it means that you're actually having a negative surplus in the equilibrium. Or basically, if you shut down the data market, you're happier. you can write this in terms of the primitives, and basically it will be if there's a high correlation with the individuals in the low value side, as you can see it here, then potentially you will get a negative surplus, which means that if I shut down the data market, probably it will be better for the society. Okay, so now I said this thing for a very specific setting. So I assume that the information leakage has this like the decrease in the mean square error, and also I assume the Gaussian distribution. Now, as long as you have those two properties that I mentioned at the beginning, the monotonicity and submodularity properties, all the results will hold. So basically what we built up is that we showed that this submodularity property hold for our information leakage definition. And then based on these two properties, we proved the results. Similarly for the inefficiency results, the main properties that we use is these two. So if you change these notations, and as long as you can show that these two properties hold, still you will have those inefficiencies and also the existence result.
Are other examples known?
Yeah, so there was the
sort of information theory measures that satisfy, these two properties as well.
I see, not just the mean squared error.
Not, yeah, so reduction in entropy.
Okay, so now the setting that I said was I have one platform and everything is known. So you can actually generalize this when the platform does not know the values and needs to design an incentive compatible mechanism in order to also learn the people value for the privacy. Also, if the correlation structure is not known, but there is a belief about it, again, the results hold. And similar results hold when there are competing platforms, but there is also one more thing about the competition. So usually we expect that the competition is going to improve the efficiency. Here, what we will see is that this is not necessarily the case. In fact, it could provide some extra causes for inefficiency, as we will see next. Okay, so I will not define the utility models again for the competition, so it will be the same with a small difference. So here I will also have like some value for joining, because we think that, for example, if a platform has more users on it, then probably it's in terms of like the value of joining, it's more beneficial, right? So for example, like if there are two social networks, one of them has more users, probably you prefer to be on the one with ignoring the privacy. In terms of joining, you will get higher value there, right? So we are going to consider a joining value function, which is monotone in the set of joined users. And then now you have two things that you should decide about, whether you want to join this platform or the other platform. For now, we assume that each user will join either of the platforms. So the value of joining is higher than not joining. And then you are also going to decide about whether you want to share your data or not. So you have two actions to think about. So these platforms are going to simultaneously offer the prices, and the users are going to simultaneously make their data sharing decision. Okay. So what we will show here is that actually this is an interesting. So with an interesting example, we actually show that a pure strategy equilibrium for joining may not exist. And however, we can look at the mixed strategy. So we can easily, you can see that if you decide to join each platform with probably 1/2, then this will be a mixed strategy equilibrium for joining. And the results that I will explain is going to be also hold if, for example, you have information leakage between the two platforms. So before I explain the theorem, let me actually give you another example. So you have two users with the correlated data, and suppose that the first user has a value less than 1. And let's for now assume that the joining value is a constant. So you will have the same joining value, which is a high value. So if I have the second user, if the second user has a very, very high value, So V2, if it is much higher than 1, under monopoly, only user 1 will share, user 2 will not share, right? Under competition, what will happen is that users join different platforms, user 1 will share, user 2 will not share. And in fact, this is going to be improving the surplus, right? So you don't have that damage of leakage from the person who had a high value for the utility. Yes.
Something, but is there value to consumers for being on the same platform?
There is a value, so we call it C, but for now, let's assume that this C is constant. So if you join the platform, you will get that value. So either this platform or the other one. But in general, you will see the condition that we need to have in order to enforce the efficiency.
There's no network effect, so I don't care how many other people are on the platform.
No, that there could be a network effect. So we will actually, so for now, let's assume for the constant in this example, but in the lemma, but in the theorem, when I explain it, there will be a condition which will be based on the externalities, like the how increasing the C function should be in terms of the user's join in order to get efficiency. That's what you want to get at.
I think so.
Yeah. So this is a good thing. Now, suppose that the value of the second user is less than 1. So now under the competition, what will happen is that, again, under monopoly, both users will share because both of them have value less than 1. And we get a good surplus. With competition, again, users will share, but they're going to join different platforms. And this is because of the leakage that will happen if you share on the same platform and the price damage that you will have if you have you're on the same platform. So in this case, what I care about is the 1 minus VI times the information leakage, right? So this 1 minus VI is positive for both of the users. And as a result, I like to increase this information leakage because that will increase the surplus. However, since they're on different platforms, I do not get that much, right? So as a result, when the value of the other one is also low, here in the competition, I'm actually losing in terms of the surplus. Okay, so now this is the result. So suppose high value users again are uncorrelated with the low value users in the first case, then the equilibrium is efficient if and only if the increase in the costs that you will get for joining by like if the set is big, the set of the users that are joining are bigger, is higher than some threshold. Okay, so basically if that joining has a higher slope, right, you are going to actually have an efficiency result. If it is not the case, you will have inefficiency result. Now, the other cases will be similar to the previous case, like the monopoly case. So suppose that there is a high-low correlation. Now, again, if the value of the high users is higher than some threshold, you will have inefficiency. And in the third case, suppose that the high-value users are correlated with at least one another high-value users. Then if the values are going to be in some mid-range, again, you will reach out to the inefficiency. So basically what we will see is that I added the competition, I expected more efficiency, and now I have a harder situation of getting that efficiency. So now the question is that what can we do? So basically you can either, like, if you know the values and also the structure, so basically you can think that I can give person specific taxes to the people to encourage them to share, and that's the Pavlovian taxes. So this is not surprising that it will improve the efficiency, but can we do something better than that? So the approach that is basically like, this is like something that needs to actually know the complete structure of the network. So that's the caveat of the approach.
Sorry, is that exactly the same criticism that you just made of the decentralized Pavlovian solution? Knowing
No, it needs to know also the values there.
I see, but it feels like, I mean, it doesn't feel like much less information. I mean, like,
if you say so. So you need to know the structure here, not the values. Okay, so the one level less, right?
Less.
So now the approach is the following. So we call it the decorrelation scheme or whitening the noise, right? So basically what you're going to do is that suppose that these are the signals, And what I will do is that I will multiply by the signals the inverse matrix of the correlations, right? So the covariance inverse multiplied by S. This will be the signals that I will output, okay? So these will be the signals that I will let the platform share. And this mediator should be somebody who actually you trust and will do this for you. Now, with this decorrelation scheme, what you can see is that Xi and S inverse, the S hat minus I have 0 correlations, and exactly because of the structure of that. And then Xi and S hat I are fully correlated, okay? So basically, what it means is that for those who are sharing, their data will be as before, their data will be, their correlation will be kept. And for those who decide not to share, it's like that you are dropping the edges for them, right? So you would only keep the correlation among those who are sharing their data. That's the implication of this whitening noise. So as a result, with the decorrelation scheme, the information leakage of an agent I will be what? It would be 0 if nobody share, if you decide not to share. And if you decide to share, it will be basically the information leakage of those people who shared similar to before, right? So I think this is a good property because you are dropping the unwanted edges. You are dropping for those who are not willing to share, you are dropping their edges to the people. This is the property of this scheme. So now what we can show is that with this scheme, the social surplus is always positive, and also it's going to be better than the previous, always better than the previous equilibrium social surplus. And high values users never contribute negative values. That's the property of it. And low value users are going to be contributing positively. And negative externalities are going to be smaller here. So we cannot show whether it guarantees the first best. So if so we could not prove that thing. And in fact, I think we have examples that we do not get the first best. So it's not still giving us the first best. So with that said, so basically in this talk, I wanted to talk about some like basic model of like data market to see like first step of how to study different properties of it. And what we saw is that when you have externalities, the prices will be depressed. And the other thing that would be very interesting to know is what sort of like intervention and regulations we should do in order to get more efficient data markets. So there are many things to be done here. This was just like one first step to like a trial on the data market. Okay, so if you have any questions, I would be happy.
We have time for one question since we're over time, but.
Yeah, so if we include like, I don't know if this is feasible for, I don't think this is feasible for every example, but if you include the, if you increase the number of observations in the data set, would it be true that that will intensify the submodularity? And if you actually include more and more observations at the end, the prices will rise to 0.
Yeah. So again, depends on the information definition, but I think for our case, yes, I think the submodularity properties hold. So as you share more and more, it's like that you have like fully correlated data that is like shared multiple. So you can think that you are adding like singletons that are like you, right, and shared every time. So I think with a similar proof, it has a submodularity property, yes, and the prices will be depleted to 0 in that case.
Okay, great. So now we have a break until 11:15, and we'll reconvene at 11:15 for more of this talk.